I always take questions at the beginning. Any questions about the home? Did you all get it? Everybody? All right. Everybody has a link to OneNote. All right. Good. Any questions at all? Because we covered just basically Maxwell's equations and the general form for propagation of plane waves, right? And now, usually like to do at least one problem, but I'll go through some theory. Did you have a question? No. Okay.
Oh yeah, 6.7.
All right, what is 6.7?
This is where you have the suppose you have the E field and the X, Y, and T equal
Wait.
of X
E field.
E field parentheses X comma Y comma T.
All right, x, y, comma t. That means it's function of x, y, and t. Go ahead.
Equals 5 cosine of pi times 10 to the 6th t minus 3.0 x plus 2y.
And what? A, z?
And so, oh yeah, AZ direction.
Okay.
Find the direction of propagation on AP and then find the H field of a function.
All right. This is a great thing to start with. I want to mention something. You see how both x and y are in there in the arguments? What I showed you last time was, let me go over this board. This is going to be a real revealing problem. It's good. In general, when you start with Maxwell's equations, when we came down, well, I'll put them up here. You don't need to write this down, but it's for everybody's sake, is equal to minus j omega mu times h. It's Michael Faraday's law of induction. And this would be sigma plus j omega epsilon times E. That's Ampere's law. Those are the two in the actual phasor form that I got from the actual relationships between D and E, H and B, and J and E. And then at that point, when you take a curl of E and you break it down, you end up with a del squared of E as such, minus really gamma squared of E equals 0. I'm abbreviating everything. We did this last time. So when we have this, we take another curl of E, then we substitute in that, then we do a vector expansion. And at this point, we assume divergence of E equals 0, rho V equals 0, which means that it's charge free, or rho V equals 0. Do you all remember this? I'm going quickly through this. So when we have this, then we moved into the assumption that the E field was, or the propagational phenomena we're talking about, is a long way from the source. And it only varies in one direction, and only has, the polarization is only in one direction too. So then from here, we ended up with getting the E field, the general form of the propagating E field, being equal to some E0 plus E to the minus gamma Z, and it's plus E0 minus E to the plus gamma Z in the AX direction. Here, this form is propagating in the plus Z direction. This is in the minus Z direction. And in general, gamma, now you have to know these things pretty well, is equal to square root of j omega mu times sigma plus j omega epsilon. That's equal to alpha plus j beta. I'm just going to give you a second. Remember this. We went through this. We developed it. You all remember how I got to that point? Just show of hands. How many do? If you don't, keep up. And remember, this stuff, it just builds. And by the time you get into chapter 5 or chapter 8, 9, and 10, a lot of this stuff, if you don't understand it here, you'll be kind of lost, in my opinion. All right, so this only has a variation spatially in Z. This one doesn't. I'm going to show you a trick with this one right here. So what do we do with this? Now, I'm going to tell you what Wentworth's book says. Did I put the solutions up for email?
There was one for like 6.3 and 6.5.
I didn't give you all. Could you send me an email? Please put up the solutions to the chapters. I'll do that for 3800 too if you're in that class, and this for all the for all the problems in the chapter, because I think it's only fair. You work all the problems, look at the solutions if you don't know how, or confirm your answers. But please struggle with these and spend a fair amount of time. All right, now this one's interesting, and I'm going to tell you the way Wentworth does it. Then I'll tell you the easy way. What Dr. Wentworth's going to do is take this and put it into the phasor domain. I'm going to do this, I'll do it right here, actually over here. So when we take anything from the time to the phasor, the E field in the phasor domain, and that's what that tilde means, just phasor domain, will only be a function of the spatial variables, not omega. By the way, I didn't say this. What is omega for this problem, and how do you know? Please, everybody, don't answer yet, just think about it. If you were asked that question, how do you find omega? Just by looking at this equation. Anyone? No. Go ahead. What do you look for?
The frequency.
Yeah, but how do you find it? Just look at it. What? It's a coefficient of t. There's a cosine of omega t. This is omega, right? You all with me? I'm trying to be clear about this. So omega is equal to pi times 10 to the 6 radians per second. From that, what is f? How would you get f?
Divided by 2 pi.
That's it, just by 2 pi. If you divide by 2 pi, you could say it's 1/2 times 10 to the 6th and hertz, or you could say 5 times 10 to the 5th, right? Hertz. Now, I'm trying to be clear about this. People miss this, trust me. Now, if I go to the phasor domain, you know, in the phasor domain, it's only going to be a function of the spatial variables. But keep watching. X, Y here. We get rid of this. It's going to have a magnitude of 5. I hope everybody agrees with that. That's the magnitude there. Now it's going to vary as what? E to the minus j. And it would be 3x minus 2y. I'll tell you why I did this one in a second. But it would have an orientation AZ. It would be volts per meter. Now this is in the phasor domain. I want you to take a look at what I did. I suppressed the omega t, right? And I made sure I had it of the form. Remember, in general, if we take a look at a propagating wave going in the plus z direction right here, the form of the E field for positive propagation will be equal to a magnitude cosine of omega t minus beta z. That's the form that you saw before, right? You'll notice that minus sign in front of z indicates the direction of propagation. Do y'all hear me on this class? I want to make sure. Everybody? Now, here's what you have to notice. This would have the phasor form E naught e to the minus j beta z ax. You'll notice there's a minus j beta times z. And because it's minus j beta, it tells me it's moving in a positive z direction. Do y'all hear me on this class? When I look here, I made sure I put a minus sign in front of here. Now if you look at that, this is 3x minus 2y. Listen to me. That's actually going to give me all the information I need about the direction of propagation. As long as that minus sign is out in front, I could factor a 3 out in front of this thing, and then you have x minus 2/3 y. But don't worry about that. Just leave it like this. Then here's what you do. Come down here and put x and y here. With me? Everybody with me on this? Now, with the minus sign out in front, simply plot, now take a look at this. If I was to look at this 3x minus 2y, right? And I want to take a look at how it's propagating. We could play a game on this one, but I can see, boy, I could actually pull this thing out, get a magnitude and stuff like this, but I'll just tell you this one. this is gonna be the actual vector sense, which would be, this vector, I'll call it, P vector here, propagation vector, is going to be going 3ax minus 2ay. And then a unit vector in the direction of propagation for this one would be, because that's the magnet, unit vector would be P vector here over magnitude P, and that would be 3ax minus 2ay over the square root, and it would be, if you look at this, it'd be 3 squared, which is 9, plus 2 squared is 4. So it's going to be the square root of 13. And that means a unit vector in the direction of propagation for this one is going to be 3 over square root of 13ax minus 2 over the square root of 13ay. And I'm just going to say something. You probably don't appreciate exactly how come I know this, but if I wanted to get a magnitude of beta, it would be that I would take 3 squared plus 2 squared square root, or square root of 13 would be the magnitude. Then I would be left with a unit vector there. After I pull out a magnitude, trust me on this one. If I pull out the square root of 13, I'm going to have 3 over square root of 13 times in the x coordinate here. Normally, this is a little advanced. Instead of having just beta scalar times the coordinates, what they actually do is they'll have, instead of having the way I've shown it here, here's what they'll do. They'll have E, this is more advanced than I really want to get into, will be some magnitude of E naught, then it'll be E to the minus J, and then you're going to get a vector that they call B vector or K vector. That means it has bx ax plus by ay plus bz az. You're just going to have to trust me on that. And then it's going to be times x ax plus y ay plus z az. So the beta becomes a vector, and the position is going to be a vector too, where it would be x ax, y ay, z az. When you dot things out, you get this, which I know this seems advanced. I don't mean to be confusing, but this is easier to see. Y'all see how I plotted this? I made sure the minus is out, right? And then I just let these things be effectively unit vectors. I went over 3 units in the x, and I went down 2 units in y. That's the vector p. That's the direction it's propagating. A unit vector would be p vector over magnitude p. With me?
So what is the direction of propagation?
Right here.
Okay.
That's a unit vector in the direction of propagation. Right? And if you look at that, and you can show it's right. Now here's how Whitmore's book does it. This is a pain. Well, he says, I know if I have E phasor, right? Curl of E right here is going to be equal to minus J omega mu times H. So curl of E right there divided by minus J omega mu is H vector. And I think he talks, does anybody know, take a look at the solution for this one? All right, if you take a look, he's going to do that, right? And then what he's going to do is this. He's going to say, I know if I have H there, that E cross H is called a pointing vector. This we haven't got to this yet, is the pointing vector. And if I take the pointing vector and divide it by magnitude of E cross H, that is a unit vector in the direction of propagation. He's going to have that. All right, that's a pain. I'm just telling you. You have to take a curl first, and then you have to go through this thing. The easiest way to get a unit vector in the direction of propagation, well, there's a couple of ways, but in my opinion, if you have something at constant frequency with a cosine form, put it in the phasor domain. That gets rid of the variation, the cosine of omega t variation. All right, so you have the magnitude, then it's e to the, you got to make sure you get a minus j there, right? Or pull the minus sign out there. And then you've got 3x minus 2y, and that will be enough information so you can simply let x and y be 1 and plot the vector p. some of this stuff is advanced, but I'm trying to show you a shortcut to get it if you want this. Now let me go and do one other thing too to finish up, because now I'm going to show you stuff that's so valuable. Pointing vector is actually power flow. What I showed you here, the E cross stage we didn't get to yet, but I will. That will give you information about the power flow, which is going to be in watts per meter squared, and the direction of propagation of power flow. What I'm going to do is, I think last time I showed you the shorthand way of avoiding curls from propagating waves, didn't I? Didn't I show you H or E can be or H can be gotten to as 1 over eta? All right, let me do this again. And I'm going to show you ways to do this problem and how. There's so many different things that are exposed in this one. This is a great problem. I can set this up, but I'm so glad you asked this. I want to cover 3 or 4 things today. This is one of them. But let me show you. And I'm going to ask the class a question too in a second. It'll really tell me if you're getting it or not. Sometimes this stuff is in one ear, out the other, unless you see it and force yourself to think about it. All right, so this is the first, some basic definitions. This is the intrinsic impedance. Do you remember the symbol for intrinsic impedance, everyone? All right. That's equal to what? The square root of j omega mu over sigma plus j omega epsilon. That's always true for constant frequency. And the units of this are ohms. Just like the units of impedance always are ohms. Okay. Now, if you look at this, if you're in the phasor domain and we're talking only about propagation, if you want the H field, and you have the E field, you take 1 over eta. Eta is a scalar term, but it has a phase, so it can have a real and imaginary part, possibly. You with me? Doesn't have to be just real, but it is a non-vector term, it's a scalar. Then it's times a unit vector in the direction of propagation crossed in the E field. With me? Also, the E field, if you have the H field, is going to be equal to minus eta, unit vector in the direction of propagation crossed into the H field of phasor domain. And let me give you a page number of what these are. There's a lot of stuff. This is on page 327. Equation 6.33. If you take a look, just for a moment, please focus on this part. These are things that people foul up all the time, I promise you. With me?
What page you say it was?
It's on page 327 in my text. Is that correct? Anybody got a text that can?
That's correct.
Yes.
Can you read it, Andrew?
Yeah.
Everybody? All right. Now, these 2 things prevent you from doing that crazy curl stuff all the time. Now remember, I showed you how to go to phasor domain from phasor to time. I don't think I showed you from time to phasor, but fundamentally the only thing you're going to do is suppress the omega t, the cosine stuff, and you over here, all this stuff gets to the exponent, e to the minus j times the remainder. You with me, class? I'm going to ask you a couple things about this. I showed you how to get the direction of propagation. If you want, well, I'll show you a couple of tricks now. This isn't my worst. Say I want the direction of propagation, I have the E field and the H field. Y'all with me? Well, there's something called a pointing vector, and I might as well tell you where it is in the book and just bring it up now, but this is a simple way to do it. Somebody might get there before me, but he did put it at the very end. I think. I guess it. This is on page 342, and he talks about the pointing vector. The one that we use all the time is equations 6.84 in the middle of page 344. Take a moment to circle that or do something to note it. And I'll put it down. It's the average power flow, and it's important. So, going back to this thing, I want to show you something. So for Poynting vector in general, now what I'm trying to do is this. There's a problem up here where the questions asked about it lend themselves to an understanding of the Poynting vector. It'll make it trivial. That's the reason I'm doing Poynting vector now, even though it's further out in the chapter. It is really a smart thing to do because this is a question you want to know how to solve that kind of a problem the easiest way. This is it. So when you think about Poynting vector, the time domain form, or the instantaneous form, is, and it's usually given as a script S. In Dr. Wentworth's book, he's going to use P, just P for this Poynting vector, but this is the typical way right here, a script S. And it's equal to E cross H. And that is in the time domain. So that would be a time domain form. Y'all with me? Normally, if we have a constant frequency, we don't deal with time domain stuff. Just like you didn't in power and stuff. You talk about the average power per cycle. You talk about average power, RMS values, and voltage, and current. This is time domain. The actual average power, power density, which is the Poynting vector, is this. And this he has in his book. P av right here is 1/2 the real part of E crossed into H conjugated. This is shown in the equation I referenced earlier. Now the nice thing about this is the units for this, both of them are going to be watts per meter squared. So it tells you the actual power density and it gives you the direction of propagation. You with me in this class? Can you see it all right, sir? If you can't see it, let me know. I'll do my best to make it right. So when we go back to this problem, you have to know how to go from the time to the phasor domain. But then, if you think about this, we can, if we have E, which we do, we can easily get H if we have a unit vector in the direction of propagation, right? Here's the beautiful thing about this. Everybody has a right hand. I think I brought this up last time, didn't I? I hope. Anyway, E, if you want to know how to find the direction of propagation, E cross H is always the direction of propagation. Remember I said that this thing is going to be a magnitude and have a vector sense to it? The vector sense is the direction of propagation. The magnitude is going to be just the magnitude of E cross H conjugated. And the vector sense is going to be what's left of E cross H. So if you want the unit vector in the direction of propagation, this is the easiest thing to do. Well, there's a couple. You can take E cross H and divide by magnitude of E cross H. That will always give you a vector in the direction of propagation. Can you all follow me in this? Now for this problem, this is the reason I don't like doing curl. When you have this problem right here, you can take that and put it in the phasor form that I have here, right? Then you can take a curl of that and get the H field, right? Curl of E would be minus J omega mu H. And then you can go ahead and say E cross H over magnitude of E cross H is a unit vector in the direction of propagation. That is more work than you need to do. That's the reason I'm showing you this. The easy way, in my opinion, is to take this and put it in terms of phasor. Does everybody know what I've done here? I'm gonna put up a problem, make sure everybody can answer the questions about that. Once you have this, you just inspect this term. Make sure that minus is out in front. And whatever is there, let x, y, and z be 1, and just plot that vector polar out. It's really the directional polarization, or the direction it's actually propagating in propagation direction. But once you do that, then you take that vector and just normalize it, make it divide everything by the magnitude, the terms, the x, y, and z components by the magnitude of the vector p, and you've got the direction of propagation. So let me give you a problem that's slightly different, and we're going to work through it based on what I've told you. Hopefully the questions that are formed in your mind, the things I ask you, you'll understand based on this, or you'll be able to answer. I'm going to go ahead and get everything in this one. So I'm going to say I have an H field. This is going to be in the time domain. It's going to be 5, and the units will be milliamps per meter. And then I'm going to have cosine of 2 pi times 10 to the 9th t plus 3z minus 2y, and it's going to be in the ax direction. Can everybody follow me on that? Now that's in the time domain. You all agree? So I'm going to start asking questions. Don't anybody answer, think. First thing I want to know, don't answer, is what is omega by inspection? Don't answer. Think. People are right. How many don't say, how many know? Does everybody know? All right, what is it?
2 pi times 10.
All right, good. What is that?
10 to 9.
Right. All right, 1 gigahertz, right? Next, I want you to take that and put it in the phasor form. All right? So, just write this down, think now as I'm going along. What is the magnitude in the phasor form of the H field? Same as before, 5 milliamps. All right. So it's going to be 5 milliamps per meter. All right. Next, what do I do? Remember, this is going to be a question Friday, this kind of thing. I put in E, right? And I know I want to put a minus J out in front. Correct, class? Please, y'all with me? You understand the reason for it? Now, what's left? Think of taking a minus out in front of this stuff. It's like minus beta z. Instead of beta z, though, you got zn1, right? So it's going to be minus, what would it be? Minus 3z, right? Follow me? Minus 3z and
Plus 2y.
plus 2y. All right, what is the orientation of the H field? This has nothing to do with orientation. This has to do with how it's propagating, what direction it's propagating. Say it's that AX, right? That's the polarization direction. It's the direction the field is oriented or polarized. Y'all with me? Now, how do you get the unit vector that it's propagating? Well, that's, I've got y and z, so I'll put y here and I'll put z here. That's the variation. We know that's spatially varying in y and z, right? With me? And if you want, I mean, I could put x, y, and z out of the board, but I'm just doing it this way. I hope you can all follow me. All right. So here I have minus 3z. And I have 2y. That is P right here. As a matter of fact, P can be represented, it's the direction, the propagational, the direction, or what do they call that? The propagational vector associated with this, not the polarization. So this is going to be minus, or really plus 2 AY minus 3 AZ. Can everybody follow me on that? Now, what's a unit vector in the direction of propagation?
Divided by square root 13.
You gotta divide it by, take the magnitude of this whole thing and divide each term, right? So I have 2 over the square root of 13 AY. It's gonna be minus 3 over the square root of 13 AZ. Okay, still not done. Now, I didn't bother seeing if what I've done here is possible in the reality we live in. But now I'm going to ask you some things, and this I haven't covered yet. So there's my waveform, and that's a unit vector in the direction of propagation. This is what I've got here, right? So what is the magnitude of beta?
2.
I'll show you a trick here. This is a little advanced, but just bear with me. What I've got right here really comes from, if I take a look at minus 3z plus 2y. This is really, if I had beta x ax plus beta y ay plus beta z az here. And I dotted it within x ax plus y ay plus z az. Right there. I mean, this would be true. Now, one thing you can take a look at, just follow me. I've literally written the vector, or I should say, yeah, the vector form of beta. This is the way it's really done. Instead of using beta x, beta y, it's usually case of x, case of y, and case of z. But this is vector beta, and this is a positional vector, x, y, and z. You with me on this, class? But it's got a vector sense. Now, do the dot product. I have beta ax dotted into xax. That's beta x times x. Do you all see that, class? Is there any beta x over here? It's 0. You all follow me, class? I want to make sure. Do you see it? All right, so ain't no beta x. Good. Next, when we have the remainder of that, we have beta ay. So it's beta y, and it's times y. And then it's plus beta z times z over here is equal to minus 3z plus 2y. Can you all follow me on this? Just take them on. You with me? Now, the reason I've done this is really the symbol for that is vector beta. And the magnitude of vector beta is the magnitude of beta. You all follow me? Can you see it's just the coefficients of x and y here? So when I look at this, magnitude of beta here is simply going to be square root of 3 squared plus 2 squared, or it's square root of 13. Can you all follow me? I know this is not part of his book, but this is important. I think it makes logical sense to bring this up now because it makes things easier in the long run, a lot easier.
Is that different from your p vector over here?
What, the beta vector?
Yeah.
Same thing. I mean, so, well, yes, it is the same thing, essentially, yes. Okay. But the reason I'm saying p there is because it shows the actual propagation direction. That's the only reason. Beta, sometimes you don't think of that as a propagation direction. This is like senior level graduate stuff that you see. Now, getting back to this, you all agree that's beta. That is beta, even though the direction isn't x or y or z. It's got a combination of lines. Now, that said, what is the phase velocity? First, it is lossless, right? How can you tell it's lossless by looking here? Anyone?
No alpha.
That's right. Alpha is 0, right? If there was an e to the minus like something Z, something Y, right? Then it's decaying, but there's no alpha available. There's no e to the minus in front of that cosine, so it is a lossless waveform. You all with me in this class? If it's lossless, what is phase velocity? I mean,
Speed
it'll
of
be
light.
true anyway. It's what? Say it again?
Speed of light. Or wait, it's gonna be,
Omega over beta. That's the reason I was cautious. I didn't calculate to make sure. Usually you start from the velocity you want and you work backward and get the other two. Here I just, threw some stuff out here. So what do we get phase velocity? Hopefully it's less than speed of light. Omega is what did you say? 2 pi times 10 to the 9th. And what is beta?
square root of 13.
Now is that less than the speed of light or not? I don't know. I think it is.
Would be 6 divided by 3.8.
What's the value? I mean, give me something times 10 to the 8th.
It's gonna be like 2.2.
Thank God. Let's see. Y'all with me while I'm doing this?
174.
1.74, go ahead. Times 10 what? Hopefully 8.
9.
It's 1.74 times 10 to the 9th. Guess what? Something's cahoots. You can't go faster than the speed of light with a real wave. What is the speed of light?
2.99.
3 times 10 to the 8, right? So this is a problem that I just winged. Here's how we make it right. Here we go. Now beta just changed in order of magnitude, so beta makes things. Beta can change anytime it wants. I mean, not beta, pardon me. Omega changed. Follow me? I just left beta the same. Now omega changed, and if omega changes, this becomes 10 to the 8, doesn't it? Sorry. And all of a sudden, now it makes sense. This is a realistic problem, isn't it, class? With me? So that's the phase velocity, you agree? Y'all follow me? Just omega over beta has to be the phase velocity by definition. We want something that's actually possible, hopefully. Even though I've seen some problems, I think in Dr. Wimmer's book, that have a violation of the speed of light limitation. But that's okay. He didn't mean to make a mistake. So that's the phase velocity in meters per second. You with me, class? Everybody understand? All right. Got the direction propagation. Now I want the E field for this right here. Let's do it over here. Guys, how do I get the E field? You want to do a curl of that to get the E field, class? Answer is no. No. You'll learn to hate curls. You do enough of them, especially in like your proloid sphere or spheroidal coordinates. How do we get the E field if we have the H field, the phase in there? We'll go to the time too. Class?
Intrinsic impedance.
All right. Well, I want to say one thing. Put the minus sign first so you don't forget. I forget minus signs all the time. It's minus the intrinsic impedance times the unit vector in the direction of propagation crossed into the H field, right? Do you agree with that, everyone? All right. So what is it for us? How do we get the intrinsic impedance? Well, it's lossless. Do you agree? Now just follow me on this. And we're going to assume it's non-magnetic. So I threw that in there at the last minute. It's non-magnetic, and Whitmer's book will have tons of non-magnetic ones. It means mu relative is equal to 1, and it's also lossless. But we got to calculate epsilon relative. So this is actually this problem is a great tool to bring all this stuff out. So, got the H field, got the direction of propagation, got the phase velocity. Now, intrinsic impedance is equal to the square root of j omega mu over sigma plus j omega epsilon. That's the general form. Agreed, class? I said one thing, that it was lossless, right? The minute you see lossless, it implies sigma is 0. Y'all with me? Just remember that. If it is lossless, sigma is 0. That means eta, notice, is j omega mu over j omega epsilon is simply square root of mu over epsilon. Agree with me? Now, that's equal to the square root of mu naught over epsilon naught times the square root of mu relative over epsilon relative. I'm doing this for a reason, so you see all the logic behind it. Apparently, at least some professors I've heard, they criticize and they say they omit steps that are not obvious to everybody. I want to make sure this is obvious. Clear? If I do something like this, just please yell at me. I will make sure everybody sees this. So if you look at this, this sticks out like a sore thumb. What is that?
Oh wait.
That is the
120
intrinsic
pi.
impedance of free space, or 120 pi. That's a gimme, so it's 120 pi. But there's this, and if it's non-magnetic, it means mu relative is 1. So it's that divided by square root of epsilon relative, right? Correct, class? Now, how can we get epsilon relative? I erased the thing down here. I said the phase velocity was equal to omega over beta, and we calculated it after I adjusted that thing to be, was it 1.74 times 10 to the 8th meters per second? Is that right?
Yeah.
Y'all remember this, class?
Yeah.
Now, it's lossless, and sigma is 0, right? That means phase velocity. If it's lossless and sigma is 0 and it's non-magnetic, phase velocity can be rendered as c over the square root of epsilon relative. I promise you can. If you want me to, I'll show you how. How many knew that? Kind of knew that? No? All right, here's how that happens. You don't need to write it down, but if you think about this, phase velocity is omega over beta, right? Well, if you look at gamma is equal to the square root of j omega mu times sigma plus j omega epsilon. Since I said it was lossless and sigma is 0, gamma here becomes just j beta, and it's equal to what? I have j times j is j squared. Square root would be j, and then it's going to be omega times omega is going to be omega squared. So j omega times square root of mu epsilon. You just watch this for a second. It means beta is equal to omega square root of mu epsilon. Can you all follow me? I'm not trying to go too fast, but I'm going to just show you that if this is gamma, alpha is 0 because sigma is 0. That means gamma is simply j beta, and then when I put sigma 0, it means it's j omega square root of mu epsilon. Now coming back over here, when I take a look at this and I want phase velocity, well, phase velocity is omega over beta is divided by omega square root of mu epsilon, right? Omegas cancel. Do you all see that, class? Now I have 1 over the square root of mu epsilon. Well, I can say that's 1 over the square root of mu naught epsilon naught, 1 over the square root of mu relative epsilon relative, right? You all agree with that? This is square root of mu naught epsilon naught. Well, what is 1 over the square root of mu naught epsilon naught, class?
Speed of light.
Speed of light, c. You all agree? And then, if it's non-magnetic, it's divided by square root of epsilon relative. That's my point. Now, we can get epsilon relative. Here's my guy, right? I can say that if I take, here's what I can do. I can say square root of epsilon relative, that's what I'm after, is equal to, and then, since I take that to the other side, I have 3 times 10 to the 8th over 1.74 times 10 to the 8th So if somebody will do this for me, we find epsilon relative for this problem I concocted is simply 3 over 1.74. You can tell me what that is? I don't know. 1.72, pardon, squared.
1.72414.
After squared?
Oh. 2.97.
Okay. 2.97. So we have that. We have, therefore we can get eta, right? Because we need eta for what we're after. Y'all with me? So if you take that, remember the square root of that is what? I think the square root is 1.74. So now I can say my eta for the region I'm talking about is going to be 120 pi over the square root of, whatever that is, 2.97. And what do you have for eta then, Russ? Anybody?
126.9.
I got 218.75.
Oh, so
120 pi is about 377. 218 sounds right. Say that again.
218.75.
218.75 ohms. Okay. Now we got everything. You see how we got epsilon to get eta. Epsilon. This is important because this kind of stuff will really throw you in a quiz. You don't know how to figure out these variables. Usually they're just handed to you. Okay. Now that I have that, how do I go ahead and get? I put the E field up here, right? If I do it. The E field, therefore, is equal to minus eta. We have that there. Unit vector in the direction of propagation crossed into H. And that's going to be minus, was it 218.75? 218.75. Unit vector in the direction of propagation, then I'd erase it.
Yeah, you erased it. Was it minus 3 over square root 13
It's,
z and then
it's minus 3, or actually, let me put the y first. So it's going to be 2ay minus 3az, both over square root of 13, right?
Yeah.
All right, and it's crossed into the H field, and the H field right there is in the AX direction. So I can put the whole thing down there, 5 milliamps per meter, and then it's going to be e to the minus j times,
minus 3z plus 2y.
I'm going to put 2y minus 3z, but you got me in the AX direction. Follow me?
This E field's in phasor, correct? Or is it?
Yeah, phasor, if it wasn't phasor, it'd be a cosine of omega t minus something, right? That's time domain. The phasor, there's no time.
Okay. But so by crossing it into the H field, which is in the phasor, it yields the E field, which is not in the phasor.
No, the E field has to be in the phasor.
Oh, okay. You just didn't
Phasor,
do it. Okay.
I mean, we're always in phasor until we multiply it by either j omega t and then take the real part.
Okay.
Y'all with me, class? All right, back to this thing. What do you get? Boy, it's a pain. I mean, I know this may seem like it's a pain, it's a long thing, but I'm trying to reveal to you all the problems that can happen. And this is a great problem to do that because I'm showing you how you get values you don't have, how you get the vector direction of. So if you look at this, the magnitude is just 218.75 and 5 with a negative sign at 5 milliamps, so it's 5 times 10 to the minus third. You can get the magnitude. Let me just put this as minus some E naught for now, all right? Now, and you got to divide that by the square root of 13, but you see we have AX, or I'm sorry, AY crossed AX is AZ, you with me? And then you're going to have another component, which is AZ crossed AX is
One.
AY. Follow me, class? So you're going to have two vector components. So maybe I should do this. If you take a look, the magnitude of this is going to be associated with these terms that I circled. Magnitude and signage. Go with me? Then, well, I can't pull that in. The two times AY crossed in AX. Y crossed into X is minus AZ. You with me, class? So this is going to have minus AZ with a 2 in front of it. Then I have AZ crossed AX is plus AY with a minus sign. Is going to be minus AY. Do you all follow me on this, class? Can you take it from there? I know I'm spending a lot of time doing this, but are you with me on this, class? If you want me to finish this, I will after class, but I've got a few things to cover. This is a great setup for how to reveal everything you need to know about going from phasor to time, and time to phasor, getting E and H, using a vector identity. Are you good with that? I don't mean to drop it like that, but I think you can take it from there, don't you? Can you guys get it? Okay. Now, I don't mean to spend that much time, but it's probably a better idea because there's a lot of things that were revealed there. So now the next thing we're going to talk about is what happens when all of a sudden you have things that are lossy to your propagational values and things and speed and all that stuff. So that he shows first he does dielectrics, then he does conductors. I'm going to do conductors first. This is section 6.4 on page 335 in your textbook. I'll do it here. It should say propagation and conductors. Is that correct? I'll check it. Hold on for 1 second. It's on page 335. Take a look. So this is kind of important too. When we talk about propagation in this, the term is good conductors. Good conductors. Good question is, what do we mean by that? So we go about it doing it this way. If you think about the actual value gamma, it's equal to the square root j omega mu sigma plus j omega epsilon. And it's equal to alpha plus j beta. Are you with me? Now, if you actually look at this stuff right here, this sigma and j omega epsilon are the coefficients of the E field when you do curl of H. So curl of H will have sigma E plus j omega epsilon E as the two terms. Do you all remember that? For a good conductor, it means this is really a current density J. A good conductor is J is much greater than this, which is magnitude of j omega epsilon E. What that implies is sigma is much greater than omega epsilon. So that's a good conductor. Can y'all follow me? Sigma is greater than omega epsilon. Omega epsilon is the coefficient of E, and this is called displacement current. Do you remember this class, displacement current density? That's displacement current density, and that's conduction current density. Just briefly, when I say displacement, I mean conduction current density. Normally what you see is what? Curl of H is equal to J plus the partial of D with respect to T. Let me just stop and talk about this. J is amps per meter squared. J is real charge moving. If somehow you could, if you looked at a bar of copper and you could spray paint an electron and watch it, it would move from one end of that bar to another if there was a voltage across it. And it would literally move and it would keep recirculating. That's real charge moving. Displacement current has nothing to do with real charge moving an appreciable distance. What happens is you have these bound charges. Say this is a dipole. Think of any kind, like in water, a dipole. Something where you have two charge centers in a molecule. When you apply an electric field, it will stretch. It will absorb energy. And then when you release the electric field or inverse the polarity, it'll go in the opposite direction. And these little bits of charges will wiggle back and forth, creating the illusion of real charge movement, but they're bound to the lattice. I mean, they're bound to an area. You can't move throughout it. That's displacement current density. And it's responsible for any kind of current that goes through a capacitor. Capacitors shouldn't allow any DC current, a good one, to flow. There might be a trickle current, but that's another story. So when we talk about conduction, a good conductor, we mean that sigma is greater than omega epsilon, usually by an order of magnitude. So when you have a good conductor, some interesting things happen, and this is important. For a good conductor, when you look at this, when you talk about the propagation constant, it's equal to square root of, this is good conductors again, square root of j omega mu times sigma plus j omega epsilon, right? But if it's a good conductor, you can get rid of that omega epsilon. So this is what it is. Can you all follow me? Now, what is, and this is where it gets interesting. Well, what is J in general? Is it J e to the J pi over 2? Isn't that what, that's one definition of J? Or square root of minus. Remember, it's magnitude 1 at an angle of 90 degrees. Do y'all remember this, class? All right, so what is the square root of J? Well, that's the square root of e to the j pi over 2, or it's e to the j pi over 4. Do you agree with that? It's e to the j 45 degrees. Do you agree with that? So I can say, what is that? That's cosine of 45 degrees plus j sine of 45 degrees. What is the cosine of 45 degrees? Value?
1 over square root 2.
And what is the sine of 45 degrees?
Same thing.
1 over square root of 2, 0.707 roughly, right? So I can say that this is 1 over the square root of 2 times 1 plus j. Now, I did that for reasons, because this way it'll become apparent. Do y'all agree with this, class? Come up here. Remember, 1 over square root of 2, 1 plus j is equal to the square root of j. There's a square root of j. So that means gamma is equal to the square root of, well, j, but the square root of j is this. So I'll just put that down. So now I have 1 over the square root of 2. And then it's 1 plus j. And then I have the square root of omega mu sigma. Well, omega is 2 pi f times mu times sigma. You can see where I'm going with this. Is going to be, and really in this case, this is going to be alpha plus j beta. We're about to see something here. And that's going to be, now I can take the square root of 2 inside there, and they cancel. And I get the square root of pi f mu sigma times 1 plus j. Now,
Wait,
say again?
I was gonna ask if you would erase that real quick.
Oh.
But I think I got it. Was it the cosine 45 degrees plus j sine 45?
Yeah, they're both 0.7, they're 1 over square root of 2.
All right.
Y'all with me? Please just follow me on this. You can see that this is alpha and beta. So alpha will be equal to beta and will be equal to the square root of pi f mu sigma. All right? For a good conductor, that's real important. So alpha equals beta. Now, another thing that's interesting is what happens to phase velocity? phase velocity is omega over beta. You agree with that? Take a look at what happens here. Well, omega is 2 pi f. And then over beta is square root of pi f mu sigma. Now, I'm putting it down before I start erasing things. I want to make sure you all follow me on this. The phase velocity is the thing that gets people. This thing's going to be a whole lot less than the speed of light. Matter of fact, at some point you can outrun the phase velocity in good metals at a certain frequency. But we'll talk about what that really means. All right, now look here for a second. Everybody with me? You can see one thing that happens. I can rewrite this. And I see I have a 2. I'll leave the 2 alone for now. On top. Then I have pi and a square root of pi. So that means I have square root of pi on top. And you can see. Then I have f and square root of f means I have the square root of f on top, right? And then I have mu and sigma downstairs, square root. So it's this. That's the phase velocity. Can you all follow me? Now, just take a look at this. What happens to it is f goes to 0 as frequency is headed towards 0.
0.
It's going to 0. All right, which means theoretically the phase velocity as you get closer and closer to really to the frequency going to 0 is almost nothing. But what does it really mean in terms of, practically speaking? Well, it doesn't mean current in wires move at something very much less than the speed of light. The actual thing about it is in a wire, a good conducting wire, whether this is getting a little further down the line, we talk about this. What happens is this. I just want you to appreciate this. We'll get into the impedance and stuff like its characteristics. Please just follow me. Suppose this is a wire and it's a good conductor. All right, but the current is flowing this way in the wire. So there's a potential plus to minus driving the current. What we're going to see is there's a skin-depth effect. All the current is going to be right on the edge of the wire, right there, right where the wire intersects free space. And it'll be all the way down there, but there will be a wave, and what actually happens is that there is going to be an electric field that is almost perpendicular to this wire, and there'll be an H field that's circulating to be in the azimuthal direction. E cross H will be the direction of propagation. That wave will be propagating at the speed of light. Are you with me? But there's also an effect where there's a theoretical E field along this axis, a very small one. And if you were to plot the magnitude of it versus depth into the wire, it would go down very quickly. It would go down, and there's something called the skin depth. How many have heard of skin depth before? All right, that we're going to talk about in 1 second. But the speed that this thing is propagating towards the center of the wire is the phase velocity that indicates. Has nothing to do with this, and that's a common mistake unless it's explained. The thing will always propagate the speed, basically, of light, unless this is a dielectric media in between, when you have electric fields propagating wires, usually you have what? You have current going down one side, coming back the other, or you have some circulating current. You have to have something like that. And that will cause this wave outside of the wire to propagate the speed of light approximately. This is important. So next, we talk about the skin depth, since I brought it up. Remember here I have alpha plus beta. Well, when we talk about the waveform, the way the wave is actually going to propagate, you're going to get an E field that is in this direction. I can call it EZ. In that direction, I'll have a magnitude E naught, e to the minus alpha, and say this direction in the center of the wire is going to be x. Boy, this is kind of a I'm not going through this in great detail. E to the minus j beta x, and beta and alpha are the same, and call this in the AZ direction. Now here's what I mean by this. This term e to the minus alpha x, and I'm saying this is the x direction, it causes the wave to decay very quickly into the wire, or the magnitude of the E field. Let me give you a visual of this in the book. I don't want to lose people on this one. So, in the book, if you take a moment and look at page 337 and then 338, at the bottom, he uses x direction and it's decaying in the z direction. That's okay, but what he's showing you is something, I hope you can see this, where he's trying to show you a variation in depth of the E field magnitude versus depth into a conducting region. Can you see that? I always think about a bar copper, or try to make it a wire copper because that's more appropriate than, I mean, honestly, things don't propagate through copper very well. They'll just short out the heartbeat. But what's going to happen is there's something called the skin depth, and this is real important what I'm about to say. So, back to this little drawing. When we have the equation for the electric field, I'll use Whitworth's notation. He says E field is going to be some E naught. Now he's talking about a plane wave in a bar of copper. It would be E to the minus alpha z, E to the minus j, beta z in the AX direction. So he's really saying, if this is z and this is x, that the E field is in the x direction, but it's going to decay like crazy. If you plot magnitude of the E field versus depth, it's going to decay very quickly. And if you come to the point right here where the E field is going to be equal to E naught, magnitude of the E field, E naught e to the minus 1, this distance right here is associated with the skin depth. So he talks about skin depth. This is the symbol we use, this element, is equal to 1 over alpha for a good conductor, and that's equal to 1 over the square root of pi f mu sigma. And it's the distance such that the magnitude of the E field right at the surface is down times e to the minus 1, or about 33%. You with me, class? That's the skin depth. So what does that mean in terms of something practical? Well, it means for wires, we can calculate the resistance of wires, the AC resistance of wires at any given frequency. And it'll change because of the skin depth. Let me try to make sure I say this part, because this is important. All right, so here's a wire, and here's the radius of the wire. Obviously, I didn't do this too well in terms of an artist's representation. Say the wire has a length L and a conductivity sigma. Can you follow me on this? And I want to know the resistance between these two ends of the wire. Well, the DC resistance of a wire is always given as proportional to length. Do you remember doing this? It's always going to be proportional to length of the wire. It's going to be inversely proportional to the conductivity of the wire. And then it's inversely proportional to the cross-sectional area. The cross-sectional area for this would be pi a squared. Does that make sense to everybody? Now, if you have something where now the skin depth is going to enter in when it becomes less than or on the same order as the actual radius of the wire. So now if the skin depth is less than A, what it really is saying is we can assume that for all intents and purposes that all the current is going to be confined, well, let's see, to one skin depth of the surface. So what it's saying is this. If I could make you imagine this, I'm not going to do a good job. If this region here is one skin depth, all the current flowing in this wire will just flow on this outer wrapper, one skin depth in thickness. It will not flow inside. That's just what happens. The wave will decay too quick. So we assume all the current is flowing in this hollow cylinder, you might say. That means our AC, therefore, is still going to be proportional to L. It'll still be inversely proportional to sigma, but now it's only the area that I've showed you, that edge area. Well, if you think about that, what is that area? Well, we can take the area of the entire thing, which is going to be pi a squared, and then we can subtract the area just inside there, which would be pi times the quantity A minus the skin depth squared. Does that make sense to you? Right? Okay, keep looking at that, and you can see that RAC, or high frequency, would be L over sigma. Now, it depends how much you want to do on this one. But if I go ahead and I expand this right here, I get pi a squared, and it's going to be minus pi a squared, and it's going to be minus pi skin depth squared, because that's skin depth. Well, skin depth is much less than the radius usually in this thing. And then there's going to be plus 2 times A times the skin depth. But really, for all intents and purposes, if the skin depth is much less than A, this becomes simply 2 pi A times the skin depth. And this will be approximately the AC resistance. Now, the thing I'm really doing is, I like to tell people this. You want to know how to think about it? You do this. Cut this thing and then unwrap it. If you pull it straight like this, the actual perimeter, the circumference, is going to be 2 pi A, correct? And the thickness is going to be what? 1 skin depth. Now it looks like a thin rectangle, right? And the area would just be 2 pi A skin depth, 2 pi A skin depth. And that'll be the AC resistance. Am I out of time yet or not? I got a few minutes?
Got one, got a minute.
A minute. All right. So he shows you examples of this on page 341, 340 and 341. With me? Now the Poynting vector is in section 6.5 in your book on page 342. But I'm planning on doing it on Wednesday. I'm going to give you some homework. Please do it. And I'll detail the problems, but I'm going to give you problems that hopefully today's material, things we cover, will directly impact all these homework problems. And what I try to do is try to do some things where you cause yourself to think about the natural questions. We've done things that very good conductors just now. We did the general form of propagation, and a direction had both Y and Z or X and Z or something like that variation. So all those things are really going to help you without doing crazy curls. You don't want to do those things. I mean, you're going to find out that they're no fun when you get into higher level. You get into coordinate systems like spherical coordinates, are really good for you. Okay. You need to see me?